Hello, I am Markus Knoche, and in this video I will present our ICCV 2025 paper Donut, a decoder-only model for trajectory prediction. In this task we are given observed agent trajectories and a graph representation of the street, and we want to predict a number of possible futures for each agent. Previous work on this task commonly uses an encoder, which takes in the historical agent trajectories and the road layout. A single-pass decoder then outputs the full future trajectory in a single step. This approach does not allow to update relations to nearby scene element during the decoding process, which limits the scene context for far future predictions. Another existing approach uses a recurrent decoder, where the future output is predicted step by step in an autoregressive manner. An issue is that the decoder has to combine feature representations from the encoder and from the decoder, and that the encoder features become outdated for far future predictions. Instead, we propose Donut, which uses a decoder-only approach to first encode the history and then uses the same model and weights to decode the future in a uniform manner. At each autoregressive step, it updates the scene context such that it is always aware of the agent's surroundings. Past and future use a consistent embedding space and they model interactions the same way. We also propose an overprediction strategy, where we ask the decoder to predict a bit further into the future at each step. An auxiliary loss on this overprediction guides the model to anticipate further into the future. The scene graph consists of polylines, which are processed by a map encoder. The historical trajectories are split into sub-trajectories at 1 Hz. Each resulting line is represented by a feature vector, together with a reference point which is used for computing the relative positional encodings. The proposer now first gathers information about the historic tokens of each agent, the surrounding map tokens, and from the other agents. Based on these, it proposes a trajectory and an overprediction. The new reference point is moved to the endpoint of the subtrajectory, and the refiner now gets relative information from these updated reference points. It refines the proposed trajectory and overprediction, and the reference point is again moved to the endpoint of the subtrajectory. We have completed a step of the prediction, and the whole process is repeated for the next time step. Both proposer and refiner use the same architecture. The previous subtrajectory is encoded with a tokenizer. Temporal attention attends to historic tokens, which are also passed to the next time step. Map attention gathers information from the map tokens from the map encoder. Social attention allows the network to see the neighboring agents. Finally, mode attention enables communication between the different modes, as we are predicting multiple trajectories for each agent. Note that this is the only difference between the history and the future, as the history is unimodal. For this reason, we give mode embeddings to the mode attention, such that it can distinguish between the different modes. A time embedding further tells the model how many multimodal steps it has already predicted, as it is expected that the modes diverge over time. All attention use relative position encodings based on the reference point. All these blocks are repeated twice, and then a detokenizer outputs the final trajectory. Even without using overprediction and refinement, Donut improves significantly over the encoder-decoder baseline. Interestingly, adding either overprediction or refinement does not improve the scores much. We observe training instabilities when training with refinement only, and we assume that overprediction has difficulties when applying it without a refiner, as the proposer would need to look into the future for about 2 seconds, which might be too much. Combining both approaches brings a significant improvement, as the overprediction stabilizes the refiner, and the refiner can do overprediction better as it uses the proposer's updated reference point, and thus the overprediction is only 1 second into the future. We achieve state-of-the-art results for the Argoverse 2 single-agent motion forecasting benchmark for non-ensemble methods. Please note that the unimodal final and average displacement errors are not well suited for evaluating multimodal forecasts, as they would be optimal with a mean prediction, which is not realistic in many situations. Qualitatively, we can also see improvement. In this scene, the encoder-decoder baseline predicts a trajectory which aims into the oncoming traffic. Donut nicely follows the road. This behavior can be explained by Donut's ability to take far future scene context much better into account. Similarly, in this scene, the encoder-decoder model hits the parked cars because it attempts to switch to the middle of the lane too early, whereas Donut keeps a safe distance. In this fairly complicated scene, the baseline fails for most trajectories, but Donut also has some difficulties. To conclude, Donut's decoder-only approach provides up-to-date relative information at each time step. It processes past and future by a unified model in a consistent embedding space. The overprediction strategy improves anticipation in each decoding step, and we achieve significant improvement over the encoder-decoder baseline and state-of-the-art results on Argoverse 2. Check out our project page, our paper, and our code on GitHub. Thank you.